Good afternoon, everyone. I'm Shahab Fatemi. At the physics department at Lunar University. I'm a plasma physicist and model developer for space plasma. Together with my colleagues, recently we have developed a comprehensive model to study the solar wind interaction with global structures of crustal magnetic fields on the moon with a very high resolution. And well, I don't think I would need to tell you in details, but you know, today Moon neither has a global magnetic fields nor has a tenuous exosphere, but instead it has crustal magnetic fields that are heterogeneously spread around the entire lunar surface with various strengths and spatial scales, as you can see from this map here. That is being observed by combination of two spacecraft observations of magnetic fields at 30 kilometer altitude above the surface. Here is the lunar far side, and to the sides are the lunar near side. And what is shown here is the strength of crustal fields at 30 kilometer altitude above the surface. The fields are highly non-dipolar and with various strengths. So it's extremely important that when it comes to the solar wind interaction with crustal fields, it creates a very fundamental and fundamental plasma physics, because the interaction in general occurs at sub-ion inertial length scales due to the small scale of the crustal magnetic fields compared to the characteristic length scales of plasma. For example, the ion gyro radius is extremely large compared to the spatial scales of these crustal fields. Nevertheless, the strength of fields are large enough that can create a surface shielding, and even a shock formation has been observed recently. Here on this picture, this is quite old, almost 10, 12 years old, from Chandrayaan observation. It shows the flux of solar wind protons that are coming off from the lunar surface, and that's the background color. And the lines show the strength of the crustal fields. You can see there is a correlation between the highest strength of crustal fields, this is the lunar far side, and the plasma, that is the solar wind protons that are coming off from the lunar surface. So in general, the take-home message here is that the interaction is kinetic, because there's a lot of kinetic processes going on, and then the kinetic processes play a crucial role. Therefore, the moon and studying the crustal field is not an MHD model. So previous kinetic simulations have focused on localized magnetic fields. For example, a series by Deca et al. And Bamford et al. They have looked at either on a single dipole interaction or with a very localized magnetic fields on the surface of the moon. We have developed Amitis. Amitis is a framework. It's a three-dimensional time-dependent hybrid model of plasma. By hybrid, I mean that's a kinetic ions and electrons are fluid, charge neutralizer fluid. I'm the developer of the code. It's a heavily parallelized code that runs on multiple graphic processing units, GPUs, for computation, that allows us to run the code with a very high, with energy efficient as well as very high resolution. We have combined it with a spherical harmonic model of lunar crustal magnetic field, the recent one by Rabat et al. There is a technical issue in here, because when we want to study the solar wind interaction with the surface, the spherical harmonics are usually underestimating the strength of the fields. Therefore, we needed to amplify the strength of the fields by a factor of 2. We have used a typical solar wind condition near the moon for various lunar phases. We have been tested for different phases of the moon as it has been moving around the Earth during the time that is in the solar wind, from the waning to the waxing time periods. And the simulation sense sizes are 15 kilometer. That's half a degree on the surface of the moon for a global state. This is an example of the crustal fields that are included into our simulation here. And as an example here, I've marked up the Reiner Gamma. And Reiner Gamma during this phase that we have been looking at, that's corresponding to day 25 in this picture to the left. Reiner Gamma was almost located at the terminator, because that's the region of our interest, to look at the localized interaction with Reiner Gamma with lunar vertex mission that I come talk about it in a minute. Here I show a classical Vega structure using our model. This is during the condition that the crustal fields are not included into the model. In the bottom, we see the plasma density, and on the top, it shows the magnitude of the magnetic field. This is a classical structure. There is nothing happening in the upstream. Solar wind is coming from the right to the left. And here we do see a cavity, as well as we do see a magnetic field enhancement that has been observed by several spacecrafts during the 60s and 70s. When we include the crustal field, however, you can see that there are a lot of disturbances happening both upstream of the moon as well as in the wake. Here we have made the color bar, the limit of our color bar such that it matches with the condition that there is no crustal field, so don't get confused by these extremely large pattern here. Those are nearly around 10, 15 nanotesla at 100 kilometers that has been sometimes observed by different spacecraft. Here we can also see a limb compression that is a plasma density enhancement that has been on and off or intermittently observed during the different lunar phases, and that is associated with the IMF orientation as well as the solar wind condition. A little bit into the detail of the structure here, what we are seeing is that we are looking at the lunar surface viewed from the sun. And in this row here, in this column here, we do see the condition that the crustal fields are not included. On top is the magnetic field. So there is no disturbance to the magnetic field, as well as no disturbances in the downgoing solar wind flux, other than the cosine solar zenith angle dependent. This is the electric field that is pointing up, and there is no reflection from the lunar surface, because when the solar wind is coming to the surface, everything impacting to the surface gets absorbed and removed. Here is for 3 different conditions that then we have included the lunar crustal fields. On top, you can see it for different lunar phases. As a tracer, I have marked the Grasimovich, and then you can see that different lunar phases, the location of Grasimovich has shifted. And you can see there are considerable perturbations and effects on the downgoing solar wind flux, especially during the condition that, for example, the South Pole Aitken Basin is located at terminator. Here on this row, we show the electric field, the contribution of electric field on both decelerating and accelerating plasma that is partially shielding, for example, the lunar surface from the incident of the solar wind. For example, we can see it very clearly here, as well as the plasma reflection. The total or the percentage of the solar wind reflection from our model is nearly 10–20%. That is also consistent with previous observations by both Chandrayaan and Artemis. We can use our model to study a very localized interaction with crustal fields as well. This is zoomed in into the Reiner Gamma that I showed you before. And we can see, and we have looked at how much for a specific lunar phase, I should mention that is here, and then for a specific solar wind condition, we do see that there is a shadow for the solar wind photon density, because the solar wind is coming from the left to the right in this picture, and the Reiner Gamma over the southern region has been capable of reducing the plasma density that is impacting the surface as well as the flux. There is also a flux reduction at different regions. So this is the why we have focused on Reiner Gamma is because with Lunar Vertex, that's the future mission, we are going to land and operate in April 2024 on Reiner Gamma, and we are going to traverse with a lander, with the rover for nearly half a kilometer in Reiner Gamma region, try to understand the pattern of the swirls as well as the crustal magnetic field. But it's extremely important for us to know how much plasma is coming down to the surface at any specific region. So if you're interested to know about the mission, I encourage you to see the poster tomorrow by David Blewett. Unfortunately, he couldn't come, but I will present it. And I would be happy to take questions if there are any in the QA session. Thank you.